Okay, let's begin. Did you all finish both of those? Nice. Well, before we look at the solutions to that, let's just recap what we did so we know what a valid answer would actually want to look like, or what we want to use last time. Last time we defined conditional probability. Probability A given B. This is the probability that A will occur given that B occurred. Probability A given B. So the definition for that was what's that going to be? Right. This was called a conditional probability. What is the probability that something will happen given that some condition has already happened? And we kind of figured out that that was the formula. We also realized that independence, we defined that. So we saw that A, B are independent if well, the probability of A given B is just the probability of A, meaning B occurring does not affect A occurring, and of course it actually goes the other way. Probability of B given A will be equal to the probability of B. We could also realize by taking advantage of this definition that also means that the probability of the intersection is the multiplication of the probabilities. Now that is not true in general, even though a lot of us like to believe that. The probability that something will happen and something else will happen at the same time. We like to multiply the probabilities, but that's actually not true. That is only true for independent events. So we put even a double if here, that's a definition. So if you want to show that something is independent, you need to show that one of these two equations hold. It can be this or it can be that. These are both definitions for the same thing. This is how we define independence. So this is something that you should have in a box somewhere. So independence means the outcome of one has no influence on the outcome of the other. It also means that if you take the probability of both happening at the same time, you multiply the probabilities. You don't always do this. And if you want the probability of A given B, it is just the probability of A. We also previously, not last class, but I think maybe a class or two before, talked about mutually exclusive events. AKA disjoint events. This means when you have two events where you look at them as subsets of your sample space, they are disjoint. They have an empty intersection. That means the intersection of A and B are 0. For disjoint mutually exclusive events, this say A, B are mutually exclusive. If and only if they cannot occur at the same time. This is the probability of A and B equals 0. That's one way that we can talk about mutual exclusivity. We can also talk about it in terms of the OR probability. The probability of A or B is equal to the probability of A plus the probability of B. That is what mutually exclusive means. Very common to mix up these two, but they're actually two very different situations. Mutually exclusive means they cannot occur at the same time. Independence means they could occur at the same time, and that's how you define the probability of them occurring at the same time. But one does not affect the other. It's not like one makes the other impossible. So here, you pull a card, you flip a coin. Whether the card lands on heads and tails has nothing to do with the card that you picked. Versus here, a situation where if you flip a coin, you can't get both heads and tails. You have to get one or the other. Getting one necessarily means you didn't get the other one. So both cannot happen at the same time. So that's mutually exclusive. So probability of the intersection is the multiplication of probabilities only in the independence case. Does not work in general. And the probability of the union is the sum of the probabilities only in the case where they're mutually exclusive. Now, in general, there are ways that we can talk about these guys in general, and this is also something that I mentioned a couple classes ago. Probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. This is called the law of disjunction. And this is true in all cases. So that's always going to be true. Right? This is the equation that relates the union and the intersection. If you are mutually exclusive, that means this is 0, and you just get the probability of the union is just the sum of the probabilities. In the event that your A and B are independent, you can have the intersection probability be given by that. So these are some general things. People always mix them up and use them when they shouldn't be using them. It happened in the two girls problem, for example. What is the probability that one's a girl and the other is a girl, and people are just like, is it a half times a half and this and that, and they try to multiply things, even in cases where they shouldn't be multiplying them. So you need to be careful with that. So and translates to multiply in the case of independence, and or translates to add in the case of mutually exclusive. The sets cannot interfere with each other. This is true in general. This is just always true at all times, including in those cases. Yes?
Is independent, did you mean to write independence? Or
A and B are independent.
no,
Is that what I wrote?
Above that, independence.
I meant to write independence. Okay, so we can talk about independence and mutual exclusivity. And okay, so we have those. Hopefully there are no questions there. We derived all of these at some point. Okay, so in the first question that you were supposed to do, problem 9 on the handout, you had to show or justify whether or not the two described events were independent, which means your answer must include that you proved one of these two equations true. If your answer does not, and you wrote something else, it's wrong, pretty much. Okay? So, let's do problem 9. Because people come up with all sorts of argument why they believe something is not independent or should be independent. But as you would have clearly seen by now, probability isn't always exactly intuitive. So just because it makes sense in some argument in your head for why something should be the case, doesn't mean that's the case. You let the rules guide you. So you want to prove something is independent, you need to show those equations. You do not know otherwise. So let's look at problem 9 on the handout. Okay, so you have all 4 aces from the standard deck. So that's the ace of clubs, the ace of spades, the ace of diamonds, the ace of hearts. You took out all the 4 aces. You shuffle them and you pick 2 at random. A is the event that the ace of spades and the ace of clubs are selected. B is the event that the ace of spades is selected. Are A and B independent? Yes?
Okay, can I say no because if we take P of A overlap B, it's going to be 0.
If you take P of A, what?
Is that what it is? The upside down U, is that overlap?
Intersect?
Intersect, sorry.
B?
It's going to be 0 in this
It's
case.
going to be 0?
Is it going to be 0 in this case? I think so, right?
That's not true. But even if it were true, what would that tell you?
Mutually exclusive.
It tells you about mutually exclusive, not independence. So even if that was true, it would have nothing to do with you answering this question. That's not true, by the way. FYI. Any other attempts? Yeah.
Yeah, I think that, or just PA given B is not equal to PA, so.
Okay, how did you find those?
Well, first I try to figure out the probability of ace of spades and clubs.
How do you do that?
Which is, well, I said 4 4 choose, or wait, it's 1 over 4 choose 2, so 1 over 6.
How did you get that?
Because like that's the number of possibilities, 4 choose 2, and then there's only 1.
How do you know? That's the only number of possibilities.
Because you're trying to choose 2 aces from 26.
Okay. So you went by talking about the total number of possibilities. By the way, that is actually the size of your sample space here, which you haven't really defined, but it seems like you're thinking about it as some sort of combination. So you said 4 choose 2. Why 4C2? Why not 4P2?
Yeah, the order of the 2 cards doesn't matter, it's just the man.
Right, the order you didn't care about, right? So you pick 2 cards, you look at them, do you have the 2 things that were described? So you don't care about the order, so you want to choose 2 cards from 4 cards. That's going to be what?
It's going to be 6.
It's 4 times 3 over 2 times 1. So that's 6. There's 6 total possibilities. Okay. And so now A, how many ways can A happen?
Only 1 way.
Only one way, right? Namely the set. So for those of you who probably are wondering, the sample space, the way he's thinking of it, is just a set of sets, right? Because he's saying that order doesn't matter. So they're just a set of possibilities that he can have. So you can have the ace of clubs and the ace of spades. You can have the ace of spades and the ace of hearts. You can have ace of hearts and the ace of clubs, etc. Right? So you can have sets of cards that you can have. So we want to create sets of size 2 from a set of size 4. Number of ways you can do that is 4 choose 2. Okay. Also, A equals 1. That's because this event that you care about is literally only one of those. You want the ace of clubs, ace of spades, and the ace of clubs to be chosen. I don't care what order in which they're chosen, but I want that particular hand to be chosen. There's only one way to get that. And so, the probability of A is going to be 1 out of 6. Now, how do you find the probability of A given B? I assume that's what you found?
Yes, so I figured out the probability of B next actually. Wow.
You found the probability of B?
Yeah,
Okay.
I found the probability of B next. And probability that you get an ace of spades is just 1 over 4 choose 1.
So tell me, how do you talk about B? How many ways could B happen?
Okay, so B was that you get 1 spade, right?
Yes, you just get the ace of spades, yes.
Yeah, so I thought that was, there's, for just choosing 1 card, that's 4 choose 1, number of possibilities of 1 card you can choose,
Okay.
which is just 4. So then, I said that there's only one of those that's an ace of spades, so 1 over 4.
You're picking 2 cards though, yeah.
Yeah, so I thought that B was just an ace of spades.
No, so the situation is you have 4 cards, you pick 2. A is this event, B is that event.
No,
Are
I thought
they
it was
the
just saying like on the first card.
No.
I thought that's what it was saying.
So you pick 2, it's just that the ace of, B is the event that the ace of spades is one of the cards that you chose.
Oh, okay.
Right? You're still picking 2 cards either way. So how would that, what would that be equal to? How many ways can B happen? What would B even look like? Yeah?
3 ways.
3 ways, what are the ways?
Spade clubs, spade
Right,
heart,
can have ace of spades, ace of clubs.
spade heart,
You can have ace of spades, ace of hearts,
and spade diamond.
ace of spades, ace of diamonds. Those are all possibilities. The number of ways B can occur are 3. This means that the probability of B is going to be equal to, well, it's the same sample space. It's 3 out of 6, so that's 1 out of 2. Okay. So those are the 2 probabilities. Now what? So I found the probability of B and probability of A. What are, yeah.
So like probability of A, it would prove that for it to be independent, probability of A given B would have to be 1/6.
Yeah. So how do you find the probability of A given B?
Well, since you chose ace of spades in B, probability of A given B, because the spades is already out,
Yeah.
is 0. Right. Because in A, you picked the ace of spades is one of the cards that you drew.
Yes.
So if B already happened, where ace of spades was drawn, then you couldn't draw the ace of spades again because it was already taken. Right? So
No, you're thinking of order. That's the problem. So no, that's not true. Because you're thinking in a certain order. You're thinking of, oh, I drew the ace of spades first, so I can't draw it again.
wasn't that was 2 events?
No, you're just taking them in order. You're not taking. There's no particular order. Yes.
And 1/3 is he changes the sample size of the space of the sample, so then only one of those works. It's probably what you have to make sure you have P is 1/3.
Okay, so what would the new sample space be?
3.
Right. Well, it's literally B. It's literally what we just said. And how many times out of that does A actually occur? 1. So the new sample space here is going to actually be B because we know B actually happened. So this is now the realm of possibilities. You ignore that. Your denominator is now 3. Now you look how many ways out of those 3 possibilities could the first possibility, A, happen. Well, it could happen 1 way. It's 1/3. So, finally, the probability of A given B is, of course, 1/3, which is not equal to 1/6, which is the probability of A. This means A, B are not independent. Moral story here, be careful, the devil is in the details. You start out by not thinking of order, you can't suddenly start thinking of order at some other point in the problem, right? I don't care what I picked first or second, or the fact that I can't choose it if it hasn't been chosen again. That's not actually applicable for the way that we were choosing. And if the probability of the intersection is 0, it doesn't tell us anything about independence, that tells us about mutual exclusivity. So, yeah, you imagine a sample space. We're just picking 2 cards at random from 4 cards. That's just a combination because I don't care about order. 6 ways that can happen. 1 way for this to happen. That's 1 out of 6 of the probability. B just means one of these cards, the ace of spades, was actually chosen. There are only 3 ways for that to happen. So out of the total 6 possibilities, there were 3 ways for that. Probability is actually a half. For A given B, this means B has already occurred. This is our new sample space. There are now 3 total possibilities. One of them is A. So that's 1/3. Turns out that these 2 aren't equal, so they are not independent. Meaning one of these actually affect the other. You can't even see from here because literally having chosen the ace of spades makes it more likely for you to get the ace of spades and any other particular card that you pick because you already have one of them. It's kind of like the 2 girls problem that way, right? Getting 2 girls is harder if you had none to begin with as opposed to if you had 1 to begin with, right? So that's these are independent and this is why. Okay, problem 10. How would that look? How did you do problem 10? Who did problem 10? Yeah?
I did a tree diagram.
Did a tree diagram? Okay, great. How did you break it up? Okay, so let's read. Newport City. 40% of the population is male, 60% is female. Of the men, 50% smoke, while 20% of the women smoke. Suppose a smoker is chosen at random. What is the probability the smoker is male? Okay. So, what does your tree diagram look like?
So you have
male and female,
Branch off, male or female.
0.4 for male, 0.6 for female.
Probability of being the M is that, probability of being the F is this.
And then for the male branch, branch off again, it's 0.5 for smoker, 0.5 for non-smoker. And then for the female branch, it's 0.2 for smoker, 0.8 for non-smoker.
Now, here we want to get a little bit technical because you're going to see. Do you want to call this S smoker? What would be the proper, if you really wanted to pay attention to detail, how would you actually describe this? Well, I didn't do A yet, but let me put it this other way. What is the given information that we have? If you have to write down the given information. We know the probability of being male, right? That's 0.4. We know the probability of being female, that's 0.6. Okay. What would I call this probability right here? Huh?
Male smoker.
What does it mean to be a male smoker? How would I describe that as a probability? Yeah.
The probability of a smoker given that you're a male.
Right. Given that you have a male, the probability that you're a smoker is 50. And given that you're a male, the probability that you're not a smoker is also 50. So this here is S given M is how you do that. Here is that. So technically these are conditionals here. And we'll see technically why that's going to matter in a little bit, but you should be aware that that's actually what you know. So the probability that if you're a female that you're smoking, so under the condition that you're female, the probability that you're a smoker is 20%. Under the condition that you are a female and you're not a smoker, that's going to be 80%. Alright, so that would be the tree diagram, that would be how it's properly labeled. How do we go about, so what is it that we want? What probability do we want? Right, given that I picked a smoker is chosen at random, so that's a condition that has already been fulfilled. We want to know what is the probability that you just chose a male. So, we're given some probabilities, we're also given some conditional probabilities, and we want to find some other conditional probability. How do we use the tree diagram to help us here? How did you finish up the problem?
The way I did it, I don't know, I did not really a technical way.
Okay, tell me what it is.
So I just said if there's 100 people, 40 of them are male, 60 of them are female, and then 20 of those are smokers, 20 of the men are smokers, and...
Okay, so you just put in some numbers here?
Yeah.
Okay, so suppose population has 100 people. So you have 40 people over here, 60 people over there, you have 20 people here, 20 people there. And 20% of 60? Was that 12?
And 58 non-smoking people.
48?
48.
Yeah, okay.
Right.
And then,
And then your probability of male given smoker is just 20 over 32.
so it's going to be 20 over well, it's 32 because you take the 20 plus the 12, right? That's fine. Here's another way to do it. Kind of like what you actually did, actually. But it's a very common thing for this kind of problem, for people to use even a table. It's very nice when you do it as well. So again, you'd suppose population is 100. And you're splitting this population into a bunch of ways. First of all, males and females, and smokers and non-smokers. So you can fill in the totals. So now I know the total number of males, that is going to be 40. Total number of females is 60. The total of the whole population is of course 100. We know that 50% of the males smoke, so this should be 0.5 times 40. So that's going to be 20 people here. And of course, this is also going to be 0.5 times 40. So that's 20 people here. Or you can think of this as 40 minus the 20 that you had here. Over here, we know that 20% of the women smoke, so 0.2 times 60. That would be our 12. The rest is 48. So we could do 0.8 times 60, or just do the 60 minus the 12. Either way, you get to 48. Now if you add up the smokers, you end up with 32 individuals, the 20 plus the 12. That's this denominator here. And if you add up the non-smokers, that's 68. Now those two should add up to 100. So both coming across here and going across there, you should add up to 100. That's how you know that you got all the numbers right. Okay. Now, when you want to say a smoker is chosen, you are choosing of the 32. And then you want to know, out of that 32 people, so you're not looking at the whole population, you're just looking at 32 out of the whole population, and 20 of those are male, which is what you want. So you have a conditional probability. What this does is it changes your sample size, right? You are no longer looking at a sample of 100, you're looking at a sample size of 32. And you can do that. And pretty much after that, the calculations will look exactly the same as right here. You say, well, the total I'm looking at is the 20 plus the 12, and the actual thing I want is the males out of that group. That's just 20, and I use that as a probability. There's another way I want to show you how to do this problem, but I'm going to have to teach you something first. But there's a very important thing. So this is a way to diagrammatically talk about a formula that I want to derive for you. It's a very important formula though. So we're definitely going to want to do this the formula way as well, which might also be helpful even when tables and tree diagrams are not. So to look at this another way, let's consider something else. Okay, so consider some set B. So we have some set B under scrutiny, we don't know what it is, and let A be any other set. I want you to note we can write B as, I can actually split B into two parts. The parts will be split thusly. The part of B that intersects with A, union the part of B that does not intersect A, or in other words, it intersects its complement. I want you to notice that we can always do that for any two sets. This is true in general. One way you can see this is, it's not a proof, but if you want like a quick visualization here, basically it's like if I have one set and another set, this is A, this is B, then if I look at the set B, I can split it into two parts. There's the part of B that is actually not intersecting with A. Right? So that's this guy. And then there's a part of B that is intersecting with A. So there are parts of B that are both in the A and the B circle. That's this guy. Notice that if I take the union of those two colors, I get the set B. This is going to always be true. Even if they were disjoint, this would still be true. That's something that's true in general, so you should know that we can do that. Another thing you should notice, also notice, B intersect A and B intersect A complement are disjoint. Because you can't have something that's in A and not in A at the same time. So these two sets that I split B into, they're disjoint. They're not connected. Now, what does that mean if I were to take the probability of the union of disjoint sets? Now recall, A1, A2 are disjoint, then the probability of A1 union A2 is going to be what? Yeah?
1.
No? Yeah?
Just B, A1 plus B.
The sum of the probabilities. It's axiom 3 of the probability axioms. Now, what does that mean for this equation? Well, if these two sets are equal, then the probability of this is equal to the probability of that. So what that means, I can write the probability of B as the probability of B intersect A plus the probability of B intersect A complement. That's always going to be true. Because I can split up any set like that, and axiom 3 from the probability axioms tells me that this is going to be true if I just take the probabilities of both sides. Now, I'm going to mix this with conditional probability, just because it's not difficult enough. Okay, so here's what we remember from probability. Let's look at B given A. Now that is going to be equal to the probability do I want the B given A? I always forget which order I want first. Okay, but it's the probability of A and B divided by the probability of A. I think that is actually the order I want, which means I can write the probability of A and B, which by the way is the same as this, to be equal to the probability of B given A times the probability of A by multiplying. Also, the probability of B given A complement, well that's the probability of B and A complement divided by the probability of A complement. So this means I can write the probability of B intersect A complement as the probability of B given A complement times the probability of A complement. Now what I want to do is I want to actually plug these into the original formula. So I have this thing. I'm going to plug that in here. And I have this thing. I'm going to plug that in here. So this means the probability of B can be expressed as the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. This is a very important formula. It looks complicated, and even if you actually say it to yourself, it will sound complicated, but if you think through it, you'll see that it makes total sense. If someone wants to figure out what is the probability of B happening, you can talk about B happening in terms of some other event all the time. So you can say, well, B is happening, well, this other event can either happen or not. So what is the probability of B happening in the event that this other thing happened? That's going to be given by this. And what is the probability of B happening in the event that the other thing didn't happen? That's going to be this. Because these are mutually exclusive events, we can split the probabilities over that. So there are two ways for B to happen. B can occur given that something else already occurred, or B can occur given that that other thing didn't occur. Right? You can always talk about that as a probability of B. Now, this equation is very important, very useful, I think, and they kind of use this on the way to proving something else, which I'm on my way to prove as well. called Bayes' theorem. But for us, I'll call this Bayes' theorem version 1, which is unofficial. No one calls it that. I'm the only one who's going to call it that. So if you look up in a textbook, no one's going to say, oh, this is Bayes' theorem version 1. I'm just going to call this Bayes' theorem version 1 because it is actually the important ingredient that makes Bayes' theorem a little bit more intuitive. So this is called Bayes' theorem version 1. And it is on our way to proving Bayes' theorem version 2, which is what everyone else just calls Bayes' theorem. But this, I think, is important in its own right, and there are a lot of problems that we can solve using that equation directly. So I thought I'd just stop it here and make that something that we probably want to know either way. So here we are going to continue to go further. Now, the probability of A given B. We know this is equal to the probability of A and B divided by the probability of B. That is by definition, nothing new there. However, I can do a very similar manipulation here. With the other way, so the probability of A given B is going to be I actually already used it here, so never mind. I'm actually going to reuse this again. So I'm going to take this and I'm going to plug in here. And I need another color. I am going to take Bayes' theorem version 2, version 1, and plug in here. So this is going to be equal to probability of the intersection. I can write this as the probability of B given A times the probability of A. Now all that, I'm going to rewrite this over, I'm going to write this entire thing in the place of probability of B. So this is going to be the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. This leads to Bayes' theorem. Version 2. Unofficial. So pretty much in most textbooks, if you look up Bayes' theorem, this is the equation they're going to tell you. And what I just showed you is where the equation came from. So they would tell you that the probability of A given B is going to be equal to the probability of B given A times the probability of A divided by the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. It's a very, very important formula. Super important. It's one of the reasons why probability is as useful as it is, and which I'll talk about a lot next time. This is called Bayes' theorem. Now I will elaborate on the significance of this formula, but for now, let's actually just put it into practice. Let's look at problem 10 again from the perspective of Bayes' theorem. Now, in problem 10, we had a city of people, some were smokers. We were given the probability of being a male was 40%. The probability 5%. The probability of, if you're a male, the chances you are a smoker is 0.5. The probability of you not being a smoker, given that you're a male, was 0.5. The probability of you being a smoker, given that you're a female, was 0.2. The probability of you not being a smoker, given that you're a female, is going to be 0.8. And we wanted the probability of, if we chose a smoker, what is the probability that they're male? Now, just by you writing down the givens, how do you know you'd want to use a formula like this? If you don't see the tree diagram later, why would a formula like this be useful? One thing you'd want to notice is that the thing you want is a conditional probability that's in the opposite order of the thing you have, right? Notice that I know S given M, I don't know M given S, right? I would like to be able to switch these two things. How can I legally switch those two things? Well, this formula is how you legally switch those two things. Notice that on the left side I have A given B, while on the right side I have B given A. So I can talk about A given B in terms of B given A, right? So when I have things flipped around, I can actually use that version, use what I currently know, to figure out what would have happened in the other if the conditions applied in the opposite order, right? So that's why we even think about using this formula. Notice we want a conditional probability in the opposite order. Of our given. So this tells us we can actually apply Bayes' theorem here to find the answer. I could just say, well, by Bayes' theorem, probability of M given S is going to be the probability of S given M times the probability of M over the probability of S given M times the probability of M plus the probability of S given, well, here your M complement is just the opposite of being a male, which in this case is female, times the probability of being female. Yep, and so now we can go in, we can plug in this stuff. So the probability of S given M, this was 0.5. Probability of being a male was 0.4 over probability of S given M was 0.5. The probability of being a male was 0.4 plus probability of S given F was 0.2 times the probability of F was 0.8. Wait, 0.6. One thing you notice, had I multiplied this out, this is going to be 0.2 over 0.2 plus 0.12, which if you multiply the top and the bottom, what you would get is 20 over 20 plus 12. That's exactly equivalent to our previous answer. So you actually get that 20 over 32. But I mean, after this point, you just plug this into your calculator to just get here. But I just wanted to show you that we actually get the answer that we figured out by other means. A lot of people think of this as something that's very confusing, but it's quite intuitive. It's literally something you can figure out with a tree diagram. You just want to write it down as a formula so you don't have to draw a tree diagram. Because sometimes your tree diagram, like I said, can have so many branches, so many different options. It's going to be confusing. You might as well want to plug it into a formula. And if your tree diagram starts out with more than 2 branches, this formula still generalizes, which I will probably talk about next time, but it's a very important formula. Here is another very common kind of example with this formula. So like I said, we're just introducing it, using it to do a few examples, but I'll talk about the significance of this formula next time because it is quite significant. the idea of the validity of a test, or the chances of some test telling you about something. Very common example. There's a rare deadly disease. 1 in 10,000 have it. You're a hypochondriac, so you think you have it. You go get tested for the disease. And the test comes back positive. Okay. So you're a little bit freaked out right now. But the doctor reassures you. She attempts anyway. Well, she says, the test can actually give a false positive. It's possible that even though it came out positive, you don't have the disease. Okay, so now you're kind of breathing easier, and she then drops the numbers to you in 1% of results. But it is 99% effective in identifying when someone has the disease. Okay, so now you're freaking out again. The question is, should you freak out? What are the chances that you have the disease? What do you guys think? Now, most people who've never taken a probability class would guess. I'm guessing around 99%. It's only wrong 1% of the time. It's right 99% of the time. I mean, there's a 99% chance you have this disease. You should go get your house in order. You know, go make up with anyone that you've wronged. Look up your will, buy life insurance, that sort of thing.
Actually, you shouldn't buy life insurance, it'll be through the roof, because you have the disease.
Oh, would you tell them?
Well,
That's
you
a
kinda have
whole
to.
other story. It's rare. Like, are they going to ask that in their forms? We don't know.
I mean,
Okay, let's.
doctor can tell them.
Okay. This is the problem at hand. What is the chance that you actually have the disease? What do you guys think? Guesses? Is it close to 99% at least? Maybe off by 1%? 98%? I don't know. What do you guys think? Let's see what Bayes thinks. Let's define some sets. Details of the event you have the disease. So of course, D complement will mean you don't have the disease. What do we want? POS test is positive. NEG test is negative. Let's write down our givens very carefully. What are we given? What do we know so far? So D complement, not, you don't have the disease. What is the information we know so far? Event someone doesn't have the disease. What are we given? What do we know? Do we know the probability of having the disease? 1 in 10,000. 1, 2, 3, 1. Okay. Which means probability of not having the disease or 1 minus that, so that's going to be 0.9999999. Okay. What else do we know from this? We know we get 1% false positive. What does it mean to have a false positive?
Test.
Probability, so it's a condition, so it means given that you don't have the disease, the test comes back positive. That's a false positive, a positive result in the event you don't have a disease. That is 1%. What is the probability of positive result given that you have the disease? 99%. What do we want? What is the event that just occurred? Well, we tested positive. What is the chance that we have the disease given we just tested positive? That's what we want to figure out. Or the chance we actually have the disease. Under the scenario that we had a positive test result. So, let's see. I don't know, it looks like, it doesn't look so good. So, by Bayes' theorem, the probability of D given POS is going to be the probability of the opposite, POS given D, times the probability of D over POS given D times the probability of D plus positive given D complement times the probability of D complement. And let's just plug in the numbers. So here we have 0.99 times 0.1231 over 0.99 times 0.1231 plus 0.01 times 9999. What is that roughly? .0098. What percentage is that? 0.98% chance. You have less than a 1% chance of having this disease. Now at first this might seem counterintuitive, but then you can start to think about it. 1 in 10,000 people have this disease. The test gets it wrong 1% of the time. What does that mean? How many times would it get it wrong? 1% of 10,000, right? Which is 100. There are 100 people that would have a false positive result, right? So this means when you test positive for the disease, it puts you in a sample space where there are 100 people, and only one of you actually have the disease. Well, 101. Okay. So now your chance of having the disease is not 99%, it's now just 1 out of 101, which is around 1%. It makes total sense if you actually think about it, but it's not where most people's minds would go in the beginning. It's very counterintuitive in the beginning, but that's when you kind of think with emotions. Oh my God, there's 99% chance that I have this disease. When you start thinking like that, you are going to mess up. Bayes helps keep you level-headed. We will continue with this next time.
That's one more.
Okay.
Yeah, I think that is.